Hi and welcome to video 1 on this part 2 from Unit 4 topic 2, and we're looking at differential equations, but we're going to be putting them into practice predominantly in the field of kinematics and working into forces and some other specific context within that area. So this first set of lessons or set of videos, which will probably be 3 or 4 videos, will be focused on differential equations in motion, so it won't quite get onto the forces yet. So there's some learning goals, success criteria there for you to have a look at. Now let's have a look at the content. So most of what follows you've seen before in methods predominantly, but also somewhat in specialist, and you will have seen some of the vectors before as well. So here's a reminder, I've put things specifically on lines. The vector quantities, position, displacement, velocity, acceleration. And then you also have scalar quantities. So displacement matches with distance, but distance is the scalar version of that. Velocity matches with speed, and similarly you also have average speed, which we'll get to, and then time as well. And acceleration is sometimes considered in a scalar way when you talk about acceleration, so it kind of flicks across between the two. But we talk about it predominantly with direction as well. So we have direction and magnitude for a vector, magnitude only for a scalar, and they're things that you should know. So just a bit of a review. Position is always the location relative to O, which is the center or the origin. Sometimes O is set, sometimes you will just set O as where it starts from, or maybe some other logical location. When I say maybe you won't use where it starts from, let's say you had a situation where somebody's dropping a stone off a cliff, you might set O as the base of the cliff, in which case the stone begins 20 meters above the base. So there's a situation. Displacement versus distance. So you'll know, hopefully, displacement is the overall distance of the object from the center. So displacement in this case is basically like position. Whereas distance, on the other hand, is the total movement that it's made. And so that diagram there shows you this particle object, it went backwards for a bit, then it came forwards. The distance is quite large, but the displacement is quite small. And velocity versus speed. So first we have velocity, that is the overall displacement over time. That's the average velocity, and it's a vector because it's displacement based, and displacement's a vector. Whereas speed is a scalar. It's the distance over time. Distance is a scalar. Time is a scalar quantity as well. In the respect of motion anyway. Certainly you can go forwards in time and backwards in time. Well, we can't go backwards in time, but you get the point. So we get a vector divided by a scalar for velocity, and we get a scalar divided by a scalar for speed. So we have velocity and speed are the instantaneous rates of change of the average velocity and the average speed. So we might talk about those 4 things: average velocity, average speed, velocity, and speed. And of course, acceleration is the rate of change, the instantaneous rate of change of velocity, dv to t, and it's also the instantaneous rate of change of velocity, which is the instantaneous rate of change of displacement x. So it's d to t of dx dt, which is d squared x dt squared. A reminder on the calculus, x is typically a function of t, although we're going to move beyond that in this series of lessons. So v is the derivative of that function of t, and a is the second derivative of that function of t, and we get some other notations such as the dx to t notation and d squared x dt squared, but also this x dot and x double dot, and it has popped up in a couple of examples that we've seen, so it's important to know that is also a representation of the calculus to get to velocity and acceleration. Note also that the integral between 2 points, which are usually 2 times because we're doing v to t, is equal to the displacement. And it's important to recognize it's a displacement here, unless you deal with the signed areas, which we've covered in math methods. So you look for the x-intercepts and make all the negative areas positive, in which case you'll be creating a distance calculation. So there's a difference there. So let's have a look quickly at example 1. So in example 1, we're given a function for velocity, which is 2t minus 4, and we're asked to find the total displacement and distance travelled by the particle after 3 seconds, where t is time in seconds and x is distance in meters. Now, we know two ways of doing this essentially. We know the way to do it with integration, and this is velocity with respect to t, so that's going to work. But we also know the way of just integrating and finding the total distance and displacement travelled. And so we might have a look at both. So first of all, let's have a look at the displacement. So displacement, that's missing an S, is equal to the integral of v to t between the two endpoints, which is 3 seconds, so 0 to 3, and that's going to be equal to the integral from 3 to 0. Very easy function, but this is of course assessing our ability to deal with the complexity of the topic, not the function. And so that's between 3 and 0 there. And if we put that in, we get 9 minus 12, and 0 goes in to give us 0, so we get negative 3 meters is our displacement. The distance, on the other hand, well, the distance is a bit different because we don't know much about the motion. But what we can do is have a look at the function here, vt equals 2t minus 4, and consider when is the velocity 0, because that'll be the x-intercept. So we want to know, when does 2t minus 4 equal 0? And that's 2t equals 4, t equals 2. So this is an x-intercept. In our traditional sense, of course, in this case, it's velocity against time, so it's actually a t-intercept. So I'll write that down there as well. But, you know, we often call them x-intercepts, so we're a bit more used to that. So that means that this function, which is linear, so it's fairly simple, and let's have a quick look at it. That means that this function actually starts below the x-axis. It starts at, the t-axis, it starts at negative 4, and it goes up and stops here. And that's 2, and that's 3. My scaling's not been very good. Now that 2 we've just worked out here. We just let v equal 0, so that's v, and that's t. So the displacement was the integral between both, and it wasn't a definite integral. Or it was a definite integral, but it wasn't an area-based calculation. And so it gave us negative 3, and negative 3 is okay for a definite integral. But the distance is not going to be that. The distance will be this area plus this area. Now we know the difference between these areas is 3 because this is the bigger one by negative 3, hence the displacement. But what I'm going to do now is use this information, that 2 there, to say that the distance, x, is equal to the integral between 2 and 0 of vt dt plus the integral between 3 and 2 of vt dt. And I'm going to be a little bit clever and put an absolute value sign around here. Now you could put an absolute value sign around both, but I know that this one is positive already, so I just need to make the other one positive. And so that is therefore, I've already done the integration, t squared minus 4t between 2 and 0 plus, and that's absolute value, plus t squared minus 4t between 3 and 2. That should say 2, so. And that's going to be equal to 2 squared minus 4 times 2, and then minus 0, plus, and that's absolute value, plus 3 squared minus 4 times 3, minus 2 squared minus 4 times 2. I think I've got enough brackets there. No, too many. There we go. And so doing that calculation really quickly, 2 squared is 4, 4 times 2 is 8, so I get negative 4, but the absolute value of negative 4 is 4, and then I get negative 3 here, and I get negative 4 there, so that gives me overall plus 1, and that gives me 5 meters. So what that's really telling me is that this object travelled backwards 4 meters and then forwards 1 meter. And that gives me my negative 3 here, but my total distance of 5 meters. Now, I could also do that by considering the integral. So where xt, the position vector, is equal to t squared minus 4t plus c. I've integrated. And then using the fact that it starts at 0, 0, times 0, it's at 0, so I put 0 equals 0 squared minus 4 times 0 plus c, and that gives me c equals 0, but also I could substitute in times and it would cancel out the c's anyway, so if I don't really know the position, that's fine. But I can put in 0 and 3, so at t equals 0, x equals 0, and I'll put in 2 as well, at t equals 2, x equals -4, and at t equals 3, x equals -3. So just check that, put that in yourself. And with that in mind, on a single axis, I can see it started here, it travelled back to -4 and forward to -3. So that's -3, and that's -4. And so I could calculate it that way as well. Although this method is much nicer for two reasons. One, for complex functions, it works out sometimes a bit easier. And two, it's a lot easier to pop in your calculator than this method here, because you've got that integral function on your calculator. Okay, so we know that displacement is equal to the integral of velocity between the two times given, and distance is the area, the signed area. So they're our important features from today's lesson. All the best.